Hello and good afternoon, good evening to everyone around the world. I love the fact that this class is so dispersed everywhere. I see folks are just coming on in. Hi, Caldrian, Glory, Brittany, Liara. It's great to see you.
I mean,
Okay. This over here. So I got this little list. How do you guys like doing this online format? Brittany, you can't hear. Let's see. If you go to the hold on, let me see if I can help Brittany here.
I can hear you now. Sorry.
Oh, what was your problem? Do you know?
It was connected to my headphones.
Oh, okay, that'll do it. Yeah, a lot of times if you have that issue right next to the mute button, there's a little arrow. If you click on that, then you can pick which sound device you're going to be going to, and that should help you out. Same thing with your video. If for some reason you're not getting your video on there. Cool. Let's see. How many folks do we have here yet? Just 8. Get a few more folks here. Now, some of you were away at a conference when we had our last session. We actually did a breakout session and just tried to grapple with just some of these basic concepts that we've been learning so far. And I'm going to go over them just briefly, just so we're all on the same page, because it's each concept builds on the next concept. So if any of you have questions while we're going along, please don't hesitate to ask. Go ahead and put it in the chat wherever. Speak it out loud. It's all good. I'm certainly interested in what you have to say and making these things kind of easier to understand. Normally I start with a quiz right at the beginning of class, but just since all we did was a breakout last time, we didn't really do a lecture, I'm going to go ahead and skip the quiz this time around. But I do want to do a little bit of a recap. So some of what we talked about so far, and again, chime in here if you've got questions. We talked about structure determines function. And where we're starting in this course, I mean, we started with the Big Bang being ultimate order and super high energy. And we learned that as the universe has been expanding, things have been going from high energy to low energy. So that gives us a direction to time and tells us the thing that's going to happen next is generally going to be lower in energy if you look at the whole system. Okay. Then we start with atomic structure, so the structure of atoms. We know an atom has protons and neutrons in the center, and that electrons inhabit orbitals outside those electrons. And there is an order to the orbitals. So if you're unfamiliar with this, or if this is new to you, make sure to jot this down, his notes. Can I get somebody to volunteer to be our class scribe for today? Eugene, do you think I can get you to do that? Eugene?
Yeah.
You think you could take notes for us today?
Okay.
Okay, great. And then when class is over, sometime tonight, go to the Moodle and go to Notes of the Class Scribe. There's a little discussion section there. Just start a new discussion with today's topic name, and then just upload your file there. It's easy to get full points, and it definitely helps your grade. So if you're talking about atomic structure, you should know the order of the shells and the orbitals. So we have orbitals composed in shells. The first shell is the one shell, and it only has an s orbital. Then second comes the two shell, that has an s orbital, and then it has three p orbitals, the px, the py, and the pz. And can anybody remember how many electrons you can have maximum in an orbital?
2.
2, right. So when you start filling in electrons, you go from the left to the right because you're going from lower energy to higher energy. And so say you had 10 electrons to fill in this puppy, your first 2 would go here, your next 2 would go in this s orbital, your next 2 would go here, so that's 2, 4, 6, that would be 8, and then that would be 10, okay? That would be neon, actually, because neon has 10 electrons and 10 protons. And so all of its orbitals are full. That means you've filled the final valence shell, okay? And we don't really have to worry about going to the third shell. If we were going to go beyond neon, there'd be an S shell. You'd have 3 p orbitals, a px, a py, and a pz, and then you'd have 5 d orbitals, d1, d2, all the way out to d5. But we're not really going to have to worry about those at all. Okay, and you can even go into a fourth shell and start adding electrons there, but we're not going to be dealing with atoms that have a high enough number of protons to really worry about this. So really, we're just focused in this area. So that's our first major concept. Need you to remember this. You'll get it on quizzes and exams. The second part is understanding how this relates to free energy. If you draw a free energy diagram and you have an unfilled valence shell, is that going to be higher in energy or lower in energy than a filled valence shell?
Higher.
Yeah, that would be higher energy. A filled valence shell, I'm just going to put an F here for filled, is much lower in energy. And this energy difference is on the order of around 70 kcal per mole. That's a huge number. It's a big difference when you fill that final valence shell. As you'll see when we deal with non-covalent interaction, they're much, much weaker. And so this is on the order of the kind of energies you would see for making covalent bonds. Because indeed, how, say we had fluorine, which has 9 electrons, so that would be 1s2, 2s2, and so we got a total of 9 electrons. We have to put 2 in our px orbital, 2 in our py orbital, and in our pz orbital, since we only have 9 electrons, it's 2, 4, 6, 8. We just have 1 here. So it just needs 1 electron to fill its final valence shell. And then it gets to drop from this unfilled energy to this filled energy, and that's going to release 70 kcals per mole of energy, which is a huge amount. So this thing is going to become very stable. And the way it does that, let's, so if we've got the fluorine nuclei here, and let's just talk about, let's see, it needs 1 electron. Where can it get that electron from? It could just steal 1 and become F minus, but it could also, we've got, say, for example, hydrogen, which has 1 proton, and then in its S shell, it's got 1 electron. It would be 1s1. It needs 1 electron to complete this valence shell, the first valence shell, okay? And so if it can get 1 electron and fluorine can get 1 electron, they'd both be a lot happier. And so what they do, if they come close enough together, they'll take their orbitals and they'll overlap them. So they just have one orbital going around both of them. So here's the hydrogen proton. Here are all the protons in the fluorine nuclei. And now this has 2 electrons in that final orbital. So fluorine gained an electron from the hydrogen, so it completed its valence shell, and it drops in energy. And this hydrogen also gets an electron in its outer valence shell, because it gets one from the fluorine, that one that was left there. And so now it has 2, it goes down in energy. So they're both really, really happy. They're both really, really stable. And this is what we call a covalent bond. That's how all things are bonded together. And you can tell how many covalent bonds something's going to make based on how many electrons it needs. So fluorine needed 1 electron, so it just needed to make 1 bond. And so you get like an FH bond like this. Right? Oxygen, on the other hand, has 8 protons, so it has 8 electrons, and so it has 0 in the pz orbital. And so it really needs to pick up 2 electrons, and so it can do it twice with water. It can do 1 orbital, get 1 proton from hydrogen, do another orbital, get another proton from hydrogen, and then you would get oxygen making 2 bonds, and that's what gives us water, okay? And on down the line, if you needed 3 electrons to complete your final valence shell, you'd make 3 bonds. Carbon needs 4, it makes 4 bonds. And so get really used to being able to draw the electron structure for any particular atom and determine how many bonds it can make. And that kind of covers atomic structure. Now there's this question of electronegativity, which we talked about on the first day and last time as well. And that has to do with this energy drop. So when you fill that final valence shell, you get this amount of energy. Okay, but fluorine only needs 1 electron. So all of that energy can pull 1 electron towards it. And so it's got a strong pull on the electron. Oxygen needs 2. It'll still drop the same amount of energy if it gets 2. So the amount of pull it has on any single electron is kind of cut in half. So minus 35 on one, minus 35 on the other. And so oxygen is a little bit less electronegative than fluorine. Nitrogen needs 3 electrons. So it's going to be the same energy drop once it's full. And so that energy is going to be divided on pulling 3 different electrons. So the amount of energy pulling on each electron is going to be 1/3 of what you saw in fluorine. And likewise, carbon needs 4. And for carbon, its atomic number is 6. So it's 1s2, 2s2, px is 2, py is 0, pz is 0. And so it needs a total of 4 electrons to complete its final valence shell. But notice it only has 4 electrons. So it would have a completed valence shell if it lost 4 electrons or if it gained 4 electrons. Either way, if it lost 4, it would have this as a completed valence shell. And it would be lower energy than if it has this unfilled valence shell. So carbon really is not electronegative. The same thing with hydrogen. Remember, it's 1s1. It can either gain 1 electron to complete its valence shell, or it can lose an electron, and then it doesn't have a half-filled valence shell. So it would actually be lower in energy without any electrons. And you see that all the time. It's just a free proton, and we call those things H pluses. And So we see those all the time. And so that's how the atomic structure leads to bonding and why one thing's more electronegative than another. Carbon and hydrogen are not electronegative. Nitrogen, oxygen, fluorine, they're progressively more electronegative because you need fewer and fewer electrons to complete its final valence shell. And the reason I re-explain this is at the end of the week, your first flip grid is going to be comparing the electronegativities of two different atoms and explaining why the electronegativity is stronger in one and not the other. So bear this stuff in mind. Why does electronegativity matter? This is where it matters a lot. So you can think of electronegativity as the pull an atom has on its electron density. And so if you had two atoms that had the same and equal pull, remember the electron density is an orbital that surrounds both of them. That's our covalent bond. Okay? If each one of these have the same electronegativity, then these electrons are going to be shared equally because they each have an equal pull. And so that would be true on a hydrogen-hydrogen bond. That would be true of an oxygen-oxygen bond. That would be true of a nitrogen-nitrogen bond because they all have the same electronegativity. So the electrons are going to be shared equally. And so that just gives you a very normal looking covalent bond. The interesting thing happens when one of these guys has more electronegativity than the other. So say we look at oxygen versus hydrogen. Okay. Which one is more electronegative?
Oxygen.
Hydrogen.
Oxygen is more electronegative, right? Because it just needs two electrons, and then you'll get minus 70 kcals per mole. Hydrogen can either gain one or lose one. So it really doesn't care. It's not electronegative. Remember, hydrogen and carbon, not electronegative. So oxygen's more electronegative. So that means it has a greater pull on an electron density, which means it's not going to be shared equally. That means the oxygen will have more of the electron density. And the way we'd show this is we'd show a bigger thing of electron density. Here's the oxygen nuclei. Here's the hydrogen nuclei. So more of the electrons are spending more of their time around that oxygen than they are around that hydrogen. And well, what does that mean? Why is that important? Well, it's so much more on the oxygen than on hydrogen that this hydrogen, you can almost see its nucleus. It's almost as if there's a hole in that density. And what charges a nucleus? What charges a proton? Protons are positively charged. So that means that if you're standing on the outside, you can actually see some of the positive charge on this proton. And so we say that this is partially positive. Okay? Because normally when the electrons are shared equally, this electron density, since it's all negatively charged, if you're on the outside looking in, you can't see the positive charge of those protons because they're shielded by this electron density. Attach an oxygen, though, something that's going to pull the electron density away from one of these atoms, and it will become partially deshielded, and you'll get this partial positive charge on that hydrogen. So whenever you have an oxygen hydrogen bond, covalent bond, you'll get a partial positive where that hydrogen is. Same thing as if you had a nitrogen hydrogen bond. Nitrogen's very electronegative. It's going to pull the electron density towards it away from the proton of the hydrogen, leaving that proton butt kind of exposed to the world. And so I'm going to draw this. This is the symbol, this funny looking S is the symbol for partial. And so you get a partial positive charge on that proton. You'd expect the same if you had FH. Fluorine is much more electronegative than hydrogen. So you'd expect a lot more electron density pulled towards the fluorine. And so this little proton over here, you'd be able to kind of see. And so you'd have a partial positive charge. These are called polar bonds because they have because the charge isn't distributed equally. It's nonpolar if the charge is equal all around it. It's polar if the charge is more in one area and less in another area. Okay. And so whenever you get an oxygen with a hydrogen or a nitrogen connected to a hydrogen, because oxygen and nitrogen are so electronegative, you get this partial positive where that proton is. This is important and should be in your notes. Why is this important? Well, atoms, in addition to trying to fill their orbitals, some of them have full orbitals that are just sticking out. So, for example, oxygen has 2 lone pairs. In other words, they have 2 p orbitals that are full, right? Remember, those are the barbell-shaped guys? So we've got 1 orbital sticking out here, and another orbital sticking out here. These are both filled with 2 electrons. They're full. And we know electrons are negatively charged. So relative to everything else, these lone pairs have partial negative charges. Well, what do positives and negatives do? What do you know about positives and negatives?
They
What do they like?
Attract.
They attract.
They attract. And so if these guys get close enough, just like 2 magnets, when you bring them close enough, boom, they start to click together, right? And so if you've got, say, another oxygen with, I'm going to draw the lone pair here, and that's a partial negative charge. If you've got an oxygen with a lone pair, that's partial negative charge, it's going to interact with this partial positive charge. They're going to attract each other, and they're going to form an attraction to each other. We call this thing a hydrogen bond. So not good at, I got to use my other thing. Hold on a second. Bond. This is how you get and why you get hydrogen bonds is because if you have a hydrogen attached to an electronegative atom, it will gain a partial positive charge, and that can interact with the partial negative charge of the lone pair of another electronegative atom. Doesn't matter which atoms these are, so long as they're electronegative. This could be an NH, because nitrogen is electronegative. The lone pair could be one of the lone pairs on a nitrogen, and you'd still get any lone pair, since it's a pair of electrons, will have a partial negative charge. And since the hydrogen's attached to our electronegative atom, this has partial positive, so you get a hydrogen bond. And so our definition for a hydrogen bond comes pretty much from this. Okay, so I'm gonna So you only see lone pairs on electronegative atoms. Okay, so you should all jot this down in your notes. Any hydrogen attached to an electronegative atom is going to get a partial positive charge, because remember that electron density is being pulled away, so you can see that nucleus, that proton butt hanging out. And this partial positive charge is going to interact with the partial negative charge on the lone pair of some other electronegative atom. Now, which electronegative atoms are we talking about? So oxygen, we said, needs 2 electrons, so we know that it makes 2 covalent bonds, and it has 2 lone pairs. Okay. Nitrogen, its atomic number is 7, so it needs 3 electrons to complete its outer valence shell. So it's going to make 3 bonds, and it has 1 lone pair. So this is going to be partially negatively charged. This oxygen is going to have 2 partial negative charges on it, because each lone pair has a partial negative charge. So each one of these partial negative charges could interact with some partial positive charge on a hydrogen if you had one around, like say attached to an oxygen. And so you get this thing we call a hydrogen bond. And for this to work, the way I like to draw this is X dash H. So this is showing the hydrogen attached to some atom X. That atom is electronegative. And then I draw these little dots to show it's making a hydrogen bond or interaction with the lone pair of another electronegative atom, Y. Okay. And X and Y both have to be electronegative, and they have to be 3.5 angstroms apart or closer. So the distance between X and Y has to be less than or equal to 3.5 angstroms. And an angstrom, just so you know, if you don't know it already, is 10 to the minus 10 meters. Okay, so these little things can make hydrogen bonds. And when you make these hydrogen bonds, you go down in energy. So if you've got unbonded here, and then you make a hydrogen bond here, you're going to go down in energy. Okay, and the amount you're going to go down when you make a hydrogen bond is anywhere between 2 to 5 kcals per mole. And I'm going to go through that when I'm going to start the water lecture now, because we got some time. I'll go over this again, but these are numbers you want to know. You want to know the distance that you need for a hydrogen bond, and you want to know the energy that you get when you make a hydrogen bond. Remember, you go lower in energy when you make this hydrogen bond.
Could you repeat the distance again?
Okay, so the distance between the 2 electronegative atoms, because remember, hydrogen's attached to 1 electronegative atom, and then you have the lone pair of another electronegative atom, it's 3.5 angstroms or less. Less than or equal to 3.5 angstroms.
Thank you.
Sure. And then the energy is between 2 to 5 kcals per mole. And you might be thinking, why do we need to know these numbers? When we do drug design later on in the course, we're going to be trying to look at how our drug interacts with a particular enzyme or protein. The way it's going to interact is by making hydrogen bonds. And so we got to look, is its hydrogen that's sticking out, is it within 3.5 angstroms of the thing that it's supposed to hydrogen bond to? And if so, can we get that amount? What amount of energy do we get? And when you sum up all those energies, that tells you a lot about how good your drug is going to bind. And so throughout the course, there's going to be a lot of like energies and distances you're going to need to know, but I'll highlight them. But it's good to take the notes and keep them on hand. So let me go ahead and switch to my fancy camera and see if I can't start. Okay, so if you download the PowerPoints for lecture 2 water, that's what I'm going to be going off of, but you don't need to, but that's what I'm going to be going off of.
So where are we starting with? Ah, yes, water. Water is probably the most important substance. If you had to name a substance on the earth, without water, we would not have life. But why is that? It's because it has a lot of unique properties. So we know the chemical structure, or at least the chemical formula for water, right? It's H2O. We've got an oxygen in the middle and 2 hydrogens sticking out on either side. We know why there's only 2 hydrogens, because oxygen needs 2 electrons to complete its final valence shell. So it's going to make 2 bonds. Hydrogen on its own needs 1 electron to complete its final valence shell. So it just needs to make 1 bond. And that works out really well. Oxygen can make bonds with 2 separate hydrogens, and everybody's happy. This, however, is not a good depiction of what the water molecule looks like. Remember our theme of structure determines function, right? This is not the structure of water. The structure of water looks more like this. That's because, remember, we have those lone pairs, right? For the oxygen, there's 2 pi orbitals that are filled with electrons. And so those actually have an effect on their structure. So if you'll see, oxygen there connected to those 2 hydrogens, and then those 2 pi orbitals sticking out as well. We call this a tetrahedral shape. And remember when we talked about bonding and between covalent bonding between something that's very electronegative and something that's not, how the electronegative atom pulls electron density towards it, leaving less electron density around the less electronegative atom. And from the other side, since there's less electron density, it's easier to see that proton core. You can almost feel that positive charge because there's a lot less electron shielding, if you will, around that nucleus. And so that gives us what we call a partial positive charge. So when you depict the structure of water, it should have partial positives by each of those by each of the hydrogens. Additionally, those pi orbitals, since those are clusters of electrons, what charge are electrons? Right? So they'll have partial negative charges. So this is the proper structure if you ever have to draw the structure of water, and you will on a number of occasions. So remember how to do it. So what happens when you put water molecules close by to each
Dr.
other?
P, can you go back
Well, if you
2
look at it,
seconds?
this water molecule
Sure.
has 2 partial positive charges and 2 partial negative charges.
What you need. What you need.
The little diagram that he just showed.
The diagram that you just had?
Oh, okay. For the water molecule.
Yes.
Yes, sir.
Yeah, hold on a second
I
here.
apologize.
Oh no, that's okay. So I think this is what you want. That it?
Thank you. I took a screenshot of it.
Okay. It's really key to draw them like this, because if you leave out the bunny ears, if you leave out these pi orbitals, then you're leaving out a key factor of what determines how it's going to function, because without those negative charges, the water molecule would function very, very differently. Okay. So,
on a number of occasions, so remember how to do it. So what happens when you put water molecules close by to each other? Well, if you look at it, this water molecule has 2 partial positive charges and 2 partial negative charges. This water molecule has 2 partial positive charges, 2 partial negative charges. What do you think they're going to do when they get close? What do we know about positives and negatives? Right? Positives and negatives attract each other, and similar charges repel each other. So the partial positive one is going to get close to the partial negative of another. They'll come nice and close like that. And that's what we call a hydrogen bond. It's those partial charges coming closer together. When things bond like that, when charges come closer together, they're lower in energy. Okay? When you make a bond, you're lower in energy than when you break a bond. And the easiest way to think about that is if something already has a bond, if you want to break that bond, what do you got to do? You got to put energy into it to break the bond, right? So that means you're lower in energy when you're bonded. You have to put energy in to break the bond. So unbonded is up here. They come together and make a bond. They're lower in energy. So similarly, with water molecules, the partial positive of one and the partial negative of another will interact. You'll be lower in energy when you do. And because you're lower in energy, because delta G is negative, that means it happens spontaneously. And so spontaneously, water will start to hydrogen bond with itself, with other water molecules. In fact, each water molecule will hydrogen bond with multiple water molecules because they each have 2 partial positives and 2 partial negative charges. Maximally, how many is that? Each water molecule can on a maximum make 4 hydrogen bonds. And you see that, but you see that in a special circumstance, that's ice. In liquid water at around room temperature, your average number of hydrogen bonds is about 2 to 3 hydrogen bonds per water molecule, or 2.5 hydrogen bonds per water molecule. Can't really have half of a bond, but some of them have 2, some of them have 3. It's only when things cool down quite a lot, the molecules stop moving around as much, that they can start to make all 4 hydrogen bonds. And to do that, they need to move slightly apart. And because they have to move slightly apart, water molecules get a little bit further apart. So each water molecule can make a hydrogen bond with each other water molecule. That means that that water is a little bit less dense. And so that's why ice floats. Ice makes 4 hydrogen bonds for each water molecule. That makes a lattice. But the atoms in that lattice, the molecules in that lattice, are a little bit further apart than normal water molecules would be, because they have to get in just the right positions to make that lattice. And that's why, since it's less dense, equal volume of ice will float in water. Okay, so now you see this property of water making hydrogen bonds. That's going to lead to a number of different properties. Remember how we talked about structure determines function, right? Well, we talked about the structure, the atomic structure of orbitals and how that leads to the function of bonding and how many bonds each atom can make. So if we look at water and its structure, we find that it can make up to four hydrogen bonds. And when you make a bond, you're lower in energy, so making these hydrogen bonds are going to be spontaneous, and so they spontaneously form these hydrogen bonds in between. This is going to lead to a wide variety of different properties. The first one would be high specific heat. Okay, do you know the definition of specific heat from chemistry? What's the definition of specific heat?
Say that again.
Say that again.
It's the heat required to raise the temperature.
Right. So it's the amount of heat required to raise 1 gram of a substance by 1 degree centigrade. For water, it takes a lot of heat to raise 1 gram of water by 1 degree Celsius. Why? Because of those hydrogen bonds. Think about what temperature is. What is temperature? Anybody know what the definition for temperature is?
How hot or cold something is?
Not quite.
Is it the amount of thermal energy inside of it?
Thermal, yes, more specifically kinetic or energy.
I know that the class that had introduction to climate change knows what temperature is. What is our definition for temperature?
Isn't it like a increase in energy, something like that? Energy in the molecules?
Something like that. So the definition of temperature is average kinetic energy. So it's how fast stuff moves around. Okay, so if you've got an atom that's cold, it's moving around a little bit, you heat it up and it's jiggling really fast. Okay, that's what temperature is. It's just how fast are these molecules moving. That's average kinetic energy. So if you think about these water molecules and the fact that they're in solution and they're hydrogen bonded to each other, between 2 to 3 hydrogen bonds per water molecule, you can think of those as little strings on each water molecule. So if you want to heat them up, if you want to raise the temperature, you put energy in, these things aren't going to be as able to move as much because they're all held down by these little strings. So you're going to have to put more energy in to get them to move around more because they're held down by the little strings, right? And if you had a different atom, like say you had octane, that's just a bunch of carbons surrounded by hydrogens. There's no polar atoms. There's no partial positive charges. There's no hydrogen bonds going on. There's no interactions between those molecules, right? And so it's really easy. You put energy in, and those molecules can start moving around willy-nilly pretty easy because they're not attached to each other. And so for octane, put in a little bit of energy, the temperature, the average kinetic energy, how much they move, goes up by a lot. That's why it's really easy to heat up octane and it turns into a gas at a very low temperature. In order for water to turn into a gas, the definition of being a gas is that you don't have these interactions between each of the molecules. You don't have any interactions, any non-covalent interactions between the molecules. So you got to break them all. So that means you got to break all the hydrogen bonds between the water molecules. Once they're not hydrogen bonded to each other, they're flying off free. That's what a gas is. And so that's why it takes a lot of energy to boil water, is because you got to break 2 to 3 hydrogen bonds per water molecule, and you may have 1 billion water molecules in your pot of water. So you got to put a lot of energy in. Now, for those of you who are interested in climate change, how does this factor of high specific heat factor into, say, climate change? Aldrian, you got any thoughts?
Wait, could you repeat that?
So how does water having this high specific heat, this property because of its hydrogen bonds, have anything to do with climate change? What does it have to do with climate change?
I'd say with it being a lot harder to raise the temperature of water than as opposed to air. Well, that was one point. What does it have to do with climate change in a sense of what, and like in terms of water, or were you just speaking in general?
Nyamungo, you got
Climate
an idea? Something you want to throw in? You're gonna have to speak up a little bit. It's hard to hear you. You'll have to speak up louder.
Yeah, I'm saying that with the high specific heat, water probably means that the water would need a lot of heat for it to increase the temperature. Then,
Okay, let me ask you this. What was the global temperature anomaly since the 1850s? Surface temperature anomaly.
1.1.
1.1. What about for the deep ocean? Remember, it was different. Temperature anomaly for the deep ocean was about 0.6 over the same time period. It's because it takes a lot longer for the ocean to warm up because it's a heat sink. You put a lot of heat into the ocean and its temperature doesn't change much. Okay. And so, one of the reasons why the temperature hasn't skyrocketed on the Earth with as much heating as we have is because it takes a lot of heat in order to raise the temperature of water. A lot easier to do so on land, right? We kind of already know that. So also for things that people are more familiar with, I'm from Chicago. In Chicago, we've got this one of the big Great Lakes, Lake Michigan. Okay. In the winter, if you go near the lake, it's a lot warmer near the lake. And in the summer, if you go near the lake, it's a lot cooler. That's because, when you come out of winter, the water has gotten really cold, right? And as you go into spring and into summer, it takes a lot of heat to warm up that lake. Well, the rest of the area on land gets a lot warmer, and we're in the middle of summertime. But that water from the lake, since there's so much of it, is still pretty cold. It takes pretty much the whole summer for the sun beating down on it to finally warm up that lake to a nice, comfortable, balmy temperature. And then by then, we're already into fall and going into winter. Well, as we hit into winter, that water's still warm. And since it's got so much heat, it's going to take a long time for that heat to dissipate out, you know, forming more of those hydrogen bonds until finally it's got 4 hydrogen bonds and it turns to ice. All that energy is being released in the surrounding environment, keeping it warmer around the lake. And so this way, lakes and oceans act as temperature buffers. They're warmer in the winter and cooler in the summer because their rate of change of temperature doesn't happen as fast because they got all those hydrogen bonds. Each water molecule can have up to 4, but in liquid water, it's between 2 and 3. You know, the higher the temperature, the fewer the hydrogen bonds. You've broken a lot of the hydrogen bonds as you go up into temperature. If you're right below boiling, maybe each one's got only 1 hydrogen bond. If you let it cool, eventually these things will form hydrogen bonds. They'll become more still. And so the temperature goes down because remember, temperature is just a measure of molecular motion. And these behaviors that you see with water are all tied to the fact that they've got, you know, as many hydrogen bonds as that they do. Okay. There's another factor called heat of vaporization. It's how much heat you have to put into water to make it into a gas. You can kind of think of it like the boiling point, right? The reason why mammals sweat, why we get sweat on our forehead when we're hot, is because that's a really efficient way to get rid of heat from the body, because water, it takes a lot of energy, a lot of heat to break all the hydrogen bonds and water molecules. Once you do, it turns into a gas and goes away and leaves with that kinetic energy and leaves with that energy. So by excreting water on our foreheads, armpits, wherever we're sweating, our body puts that energy in, breaks those hydrogen bonds until they float away as a gas. And then that takes the energy away from our body and, you know, into the surrounding area. If we used a different liquid that didn't have as many hydrogen bonds, it wouldn't work as efficiently. If there's not a lot of interconnections between the liquid molecules, it's a lot easier to turn them into a gas, and so it doesn't take as much energy with them. And so it wouldn't be very good at cooling. So water is essential for life as we know it, and it's all because of its unique structure and because of the structure, the fact that one of the atoms is very electronegative and the other 2 atoms are not, and it's got those lone pairs, and so it's got partial positive charges and partial negative charges. So that makes it all really, really kind of unique in terms of its shape, but it gives those features that it's going to have. So you got that high heat of vaporization, high specific heat. Those are 2 features of water that are direct consequences of the number of hydrogen bonds that it can make. You got questions that might help you understand better? No? Does everybody?
No questions.
You think you think you understand the idea? Or you need some time to percolate on it, or it's confusing?
I need a little bit more time to understand the electronegativity and like the
Okay.
diagram.
Okay. And if anybody wants, they come to my office during office hours or shoot me an email. We can do a one-on-one Zoom. I want to make sure that you understand it as we go into the next stuff, because electronegativity is super important. Now, when you look at atoms and structures and proteins, it's the atom. Basically what you're looking for is which atoms are electronegative and which ones aren't. And so just always remember, your nitrogens and your oxygens are electronegative, carbons and hydrogens are not. That's the take-home message. But I'll take more questions on Friday. But before then, if anybody wants to Zoom or chat about stuff, I'm happy to explain anything.
Dr. Vanessa, I will be, I'm gonna email you.
Okay, good.
Okay.
I'm happy to. Okay. Anyone else? How are you guys all feeling? Okay. I think what I'm gonna
So
do,
need
you need some help, Glory?
yes, Rob. I think I need more explanation on this heat, specific heat,
Okay,
and
okay.
its interaction. Mm,
We can do, I'll send you an email. We can set up a time that's gonna work for you.
with climate change.
Okay, I'll send you an email, and we can set up a time
Okay,
either today or
I'll send you an
tomorrow.
email, and we can set up a time today or tomorrow.
Okay, everybody, have a great day, and I'll have this lecture up on YouTube pretty soon. And Moodle.
On YouTube pretty soon. And Moodle.